This video is brought to you by the ILC. Since we have an equation relating some variables, and we're dealing with rates that are about those variables, we're probably dealing with a related rates problem. So, how do we solve a related rates problem? And what I like to do first is identify what we know and what we want to know. So I know that the electrical system is the current of the electrical system is decreasing at a rate of 8 amps per second. And I is the current, so in other words, di dt is equal to -8, and I use negative because it's decreasing. Furthermore, the voltage remains constant at 24 volts, so since it's not changing, I can say V is equal to 24. Since V is the voltage. And we're asking what rate the resistance is increasing. Say we want to know D and the resistance is R, so dR dt. That's what we want to know, so I'll put a question mark there. Now, you may notice they say at what rate is the resistance increasing when the current is 56 amps. So the resistance is increasing at variable numbers at different times. It's not just increasing or decreasing, for that matter, at a constant rate, so we have to account for that fact. We have a certain point in time that we care about, specifically when the current is 56 amps. That's the time we want to find the rate. So the way I express this is I say the instant value we care about is at 56 amps. So what is that is the current, so for us that's I is equal to 56. Alright, now the equation relating all these variables is V is equal to I R. Now I know V is just 24. Now since that doesn't change, it's always 24, I can substitute that. So 24 equals IR. Notice I and R are changing over time, and thus I leave them as I and R. Now when I take the derivative of this equation, because we can't substitute this 56 because it's an instant value into the equation until we take the derivative, when I take that derivative, I get 0 equals, and we have to use product rule and IR here, I get R di dt plus I dr dt. Oops, let's make sure that's a capital R there. Remember, we're trying to find dr dt. That means I'll need to substitute in for every other variable in this equation. And we can think of di dt as one big variable, and same with the rest of the derivatives. So I is a variable, we can substitute for that. di dt is -8 at that time, and constantly in fact. R, however, we do not know. Now note that whatever R we find here is an instant value, because again, these numbers are changing. I and R change over time. They'll have their own graphs, so whatever they look like. With I or R with respect to t. So we need to find R is equal to some number as an instant value. Now if you want to find a constant instant value, right, not a rate, but an instant value at one of the base variables, we just take the variables we do know and substitute them into the equation that we do know, right here. So this is when we substitute the variables we know, the instant value specifically, into the equation. Note that we didn't substitute it in before we took the derivative, because that would be incorrect. Alright, so 24 then, when we substitute I, we get equals 56R. When we divide, we get R is equal to 24 over 56, which can be reduced to 3/7. Alright, now we can substitute every value in to this equation here. That is, every value except for dr dt, because that's what we're trying to find. We have 3/7 times di dt, which is -8, plus I, which was 56, dr dt. That's what we're trying to find. Now we solve this like a regular arithmetic equation. I'm going to multiply this -8 to this 3/7 to get -24/7 and move it to the other side to get positive 24/7. That's equal to 56 dr dt. We can then divide by 56 and get 24/7 and times 1 over 56. We already know this reduces to 3/7, so what this is 3/49, and this is equal to dr dt. Now that we know what this is equal to, we have our answer, which is 3/49. We need some units on this, however, in ohms per second. They give us the unit. So we'd say ohms per second, and I think ohms is a little symbol here. I'm going to write it out, just to be safe. And that would be our final answer.